In this lecture, we will discuss a particular example to solve a simultaneous linear differential equation, and that should be the last lecture for the simultaneous linear differential equation. In the previous lecture of a simultaneous linear differential equation, we have already learned the concept if the right hand side of a simultaneous differential equation becomes 0. In this particular lecture, we will learn if the right hand side should not be a 0. That means both the equations should not be in the homogeneous form. Then how can I solve this linear simultaneous differential equation? So here I take an example to solve a simultaneous linear differential equation. This one is the first equation and this one is the second equation. Okay, these two are two equations. So when we move to the solution part of this differential equation, first we write the first equation in using D, where D stand for d dt. D stand for d dt because here t is the independent variable and x and y is the dependent variable. So this one is D stand for dt t. Okay, so if we write D stand for ddt, then dx dt becomes dx dt becomes capital Dx minus 5x plus y equals to e to the power t. Then this equation should be written in that form: d minus of 5x plus y e to the power t. For the second equation, it's become capital Dy minus x plus 3y. That means minus x plus d plus 3y equals to e to the power 3t. Again we use the method to eliminate either x or y. If we want to delete the x, if we want to eliminate x from these two equations, in that case you should consider first equation is multiplied by 1 and the second equation is operated by d minus 5. Exactly for that reason here we write the operating on both sides of 2 by d plus 5 we get. Keep up this one, d minus 5x plus d plus 5 into d plus 3y equals to d plus 5 e to the power 2t. What represent d plus 5? It's represent differentiation with respect to t 1 times plus 5. If we differentiate e to the power 2t 1 times, it's become 2 e to the power 2t, and 5 into e to the power t, it's become 5 e to the power 2t. So the ultimate result should be 7 e to the power 2t. If we add equation 1 and 3, in that case the result d minus 5x should cancel out from this equation. D minus 5 should cancel out from these two equations, and the remaining equation becomes, when we multiply this result, d plus 5 into d plus 3, d square plus 8d plus 15, here it is 1, so it's become 16. That means d square plus 8d plus 16, it's a square term of d plus 4 the whole square, so here we use d plus 4 the whole square y. In the right hand side of the first equation is e to the power t, so here we write e to the power t, and the second equation is e to the power, in the second equation it is 7 e to the power t, e to the power 2t, so here we write 5 e to the power t plus 7 e to the power 2t. Okay, next when we find the solution of y, now it's become a linear differential equation with constant coefficient, so we have to solve in two different part. One is for complementary function and the another one is for particular integral. Okay, so when we find the complementary function, you can easily observe that if we replace d by m, the result should be -4 and -4, and it's represent that the root are -4 -4. So the complementary function becomes c1 plus c2. It's the norms when the root occur and the same root occur and the root are the real root. In that case, we write the complementary function is c1 plus c2t e to the power -40, because -4 is the root. So when we find the particular integral, in that case the result should be, here fd is d plus 2 d plus 4 the whole square, so here we write d plus 4 the whole square, and the right hand side is e to the power t plus 7 e to the power 2, so here we write e to the power t plus 7 e to the power 2t. We just separate this quantity, 1 by d plus 4 the whole square e to the power t plus 7 is a constant term out from the operator, 1 by d plus 4 the whole square e to the power 2t. Okay, so what is the procedure when the right hand side is a function of e to the power t? So here we remember the procedure is, if 1 by fd we operate e to the power at, e to the power at, the result becomes, replace d by a, so the result should be f a e to the power a t, provided this f1 should not be 0, that is not equals to 0. You can apply these norms only when f1 is not equals to 0. Exactly for that reason, here a is 1, so we replace d by 1, the result becomes 1 plus 4 the whole square, that is 25, which is not equals to 0, so you can put here. Similarly, where we put d equals to 2, the result becomes 2 plus of 4. It's a wrong calculation, it should be 2, it should be 2, it's not 1, it should be 2. 2 plus 4 the whole square, that is 36, so the result becomes 1 by 7 by 36 e to the power 2t. So it's your pi and it's your cf. So the solution regarding y should be, cf plus pi, that is cf is c1 plus c2t, which is mentioned here, and pi is here. So here we write the result 1 by 25 e to the power t, 7 by 36 e to the power 2t. Okay, so what should be dy? Why we find the dy portion? It's very important. If we use this result in that equation, you have to find the value of x, then what should be the suitable case you choose? In that case, you should always prefer to find the value of x should be equation 2, because if we want to choose equation 1, in that case you have to find cf as well as pi. But if we put here the value of y here, in that case you can find the x directly. Exactly for that reason we put the value of y in equation number 2. Okay, you can also put the value of y in equation 1. In that case your calculation should be laborious, so delete the work of too many work. For that reason we use the value of y in equation 2. I think it's clear for you. So if we put here, you have to require the value of dy. Exactly for that reason we find the value of dy from this, differentiate this result, c1 plus c2t e to the power -40, the result becomes this, and this one becomes this. because differentiation of e to the power 2t is 2 e to the power 2t, so 2 in 2 by 36, it's become 1 by 18. E to the power 2t differentiation is e to the power 2t, and when we differentiate c1 plus c2, and the result becomes only c2. Exactly for that reason here we write c2 e to the power minus 40, and when we differentiate this one e to the power minus 40, the result becomes minus 4 c1 plus c2t e to the power minus 40. Put this value in equation 2, we got the result of x becomes dy plus 3y minus e to the power 2t. Putting the value of dy from this equation number 6, we get the result of x, and the required solution is to write the result of x as well as the result of y. Okay, that should be the parametric form of the given equation. When the equation given simultaneous linear differential equation, you always find the solution of this equation in the parametric form. So that is enough for the simultaneous linear differential equation. One topic is remaining for your class. It is the application of the differential equation. So wait for the next lecture for application of the linear differential equation, why we study linear differential equation and where we apply the linear differential equation. Exactly for that reason we use the